Hello guys, good evening. Can you hear me? Audible? Yeah, just give me a minute. Okay, so guys, today we are going to start a new chapter, that is thermodynamics, right? Okay, so see what is this chapter is all about? Thermodynamics. Thermodynamics is a chapter that deals with the motion of motion of heat, basically flow of heat or flow of energy, we can say. Okay, the term you see, thermodynamics. Thermo stands for heat, and dynamics is nothing but motion or flow. Correct? Motion or flow. So basically, we are going to understand about the heat energy, the flow of heat energy, how it flows, and the various factors associated with it. Correct? So in this chapter, we are going to understand about the energy of a system, means all kind of energy we'll see, uh, enthalpy, heat, work, all these terms we are going to understand. And we also understand here about the feasibility of a reaction, right? We also discuss about the feasibility of a reaction. We are also going to understand about, like I said, various energy terms, and we also discuss about the various processes. All these things we are going to discuss in this chapter. We started, Anurag, we started with thermodynamics. Okay, just now we started. Okay. Yeah. So feasibility of a reaction, like, there are, yeah, Anurag, everything is fine. Not a problem. Yeah. Thank you. So we are going to discuss about all these things in this chapter. Okay. So, like, any reaction if you have, so all these reactions to proceed, we must have certain condition, correct? We cannot say a given reaction is possible in all conditions. We must have a minimum value of pressure, minimum value of temperature, and under a given set of conditions, a given reaction is possible. Okay, so the feasibility of reaction is nothing but this only, like under a given set of condition, whether the reaction is possible or not, right? So if the reaction is taking place, then what is the minimum and necessary condition for that, right? That we call it as the feasibility of a reaction. So this we are going to understand in this chapter. Okay, we are going to discuss about gives free energy, and from that only we can say the reaction is feasible or not. Correct? So first of all, in this chapter, all these things we are going to discuss. There are two sections on this chapter we have. We also discuss about thermochemistry here, right? Thermochemistry is a second section we have into this. Okay, here we discuss about the various enthalpy, various types of enthalpy, enthalpy of formation, enthalpy of combustion, and all those things. Correct? Two chapters, two sections we have in this chapter: thermodynamics, which deals with all these things, and thermochemistry, which mainly deals with the enthalpy of different types of processes. Okay, and that we'll discuss. So this chapter is this part is a bit small, smaller one than this one. This one we have to discuss a lot of things. Okay, so this chapter we are going to study in these two sections. Okay, one is thermodynamics, which deals with all these three things, and the second part is thermochemistry. First we'll finish this, and then we'll move on to the second part of it. Okay, so what is thermodynamics? In this chapter, write down, all of you, chemical thermodynamics. Chemical thermodynamics is the branch of physical chemistry which deals with I'll go back, Charan, just a second. Let me finish this. Branch of physical chemistry which deals with the transport of heat either as a result of physical change or as a result of chemical change. Anything will be there. Chemical change, physical change or chemical change. Copy this down, then I'll go back. Done? Okay. So guys, in this chapter, we are going to use different terms here, right, that we haven't studied before, okay, till now. So we are going to see some new terms here which we'll use in this entire chapter, correct? And there are so many terms, so many processes we need to understand, which we'll very frequently use in this entire chapter. So today's session is mostly about that in the introduction of the entire thermodynamics. Okay, you must be thinking, okay, 3.5 hour only introduction, no, it's too much, right? But the thing is like that only. We are going to understand what is system, what is surroundings, you know, then what types of system we have, what is the boundary. Okay, we are going to understand about the variables, right? How, what are processes, what are different types of process we have, and the entire understanding of that entire process, correct? Then again we'll discuss work, what is heat, what is internal energy, right? After understanding all these things, right, thermodynamic properties we'll see what is state function, what is path functions. So these are, you can say, concepts are there, but these are the terms that we use in this chapter. So first of all, you have to be familiar with all these terms, because we'll be using these terms very frequently in this entire chapter. Yes, cyclic process also we'll discuss under processes. So just one small definition we have of this. Okay, that is cyclic process. So like I said, first we need to understand the various terms that we have here. So all of you write down the heading, terms used in thermodynamics, or simply you can write down terms used. Okay. First thing we'll see, what is a system? You must have done this in physics, right? This chapter, thermodynamics, right? Remember, this chapter in chemistry, it is different from the one that you did in physics. Means convention is also different. Okay. Yeah. Write down system. What is a system? It is the specified part of universe which is under consideration or investigation. Which is under consideration or investigation. Part of universe. Okay, second term. I'll explain this just a second. Second term, we have surroundings. Surroundings. All other matters which interacts with a system, and a part of universe. And obviously it is a part of universe only, but we'll write down this. All other matters which interacts with system and a part of universe is called surroundings. Is called surroundings. Okay. And if you consider all these things together, system and surroundings, collectively it gives universe, right? The system and surroundings both are the part of universe actually. Copy this down. Okay, done all of you? Yeah. See, the understanding of this, the best example we have, suppose the pen is there in your hand, right? If you try to understand about the energy of the pen, or if you're considering the pen for a second, right? This pen becomes a system for you. An entire other thing is the surroundings. Okay. Suppose you are sitting in the class and the teacher asks you that you have done the homework or not. So you become the system for that point of time. And the entire other thing, including the teacher, is a surroundings. Okay. So system plus surroundings collectively gives you universe. Okay. System is the one or is the thing which is under consideration at any point of time. Correct. So suppose you have the universe. Universe is this, correct? And in this universe, obviously there are so many things present. But what we are doing, it depends upon you, Madhav. It depends what you are considering at that point of time. Okay. Anything. It's totally depends upon you. If I'm talking about the bird that is flying over there, the bird becomes the system for me for that point of time. Okay. So it's completely, based on the person, like based on the individual. Whatever you are considering, that becomes a system for you at that point of time. Correct. So this is the universe we have. And in this universe, like I said, there are so many things, but I'm considering only this, beaker in which the gaseous particles are present. Okay. So I'm trying to understand the motion or the energy of these gases, correct? So this gas particles becomes the system for me, okay? And the entire other thing is the surroundings. Surroundings, correct? This wall you see, the wall of the container that you have, this wall separates the system and surroundings. So this we call it as the boundary. Did you get it? So what does this boundary do? This boundary separates the system and surroundings. Clear? Now, this boundary, you see, there are a few things about this boundary. This boundary can be fixed. We can have fixed boundary. We can have movable boundary. That is also possible. I'll give you the example. We can have imaginary boundary. We can also have real boundary, right? We can have, adiabatic boundary. Adiabatic, and one more we have diathermic boundary. Like I said, we have so many terms here. So these terms you need to understand. Okay, what is fixed boundary? What is movable boundary? what is imaginary, what is real, diathermic, adiabatic. All these things we need to understand. No, it's not. System is this gas particle, right? Boundary is this. So if the boundary is moving, either it is compression or expansion, the system is the gas particle only. It's a different thing that it will occupy a different volume. But still we are considering the gaseous particle. The container is not the system. Are you getting it? Copy this down. Yeah, one second, I'm done. Just a second. We'll discuss this. What these terms we have, we'll discuss. Suppose we have a cylinder like this, correct? Open end we are considering. It's fine. Open end cylinder we have. Now what we do, we fix a piston into it. Have you seen the the air pump which you use to fill air into that tube, bicycle tube, right? Have you seen that? Yes. So that kind of system you assume. That kind of system you assume. The down part we have a cylinder and a pump attached to it. So this is the, it is a cylinder and a piston. So you can consider cylinder and piston system is the cycle pump, considering like that. Okay. So we have this. Suppose this is the piston we have, correct? Now it totally depends on us what we want to take, correct? In this chapter, there are so many assumptions. Whatever chapter you have done so far, this is the most difficult chapter. Difficult not in the sense of you won't understand the concept. Okay, when I explain things, you will understand the concept properly. You'll feel like, okay, I'll understand. But there are conditions. There are so many conditions that we are going to use. So you have to keep that in mind. So under this condition, this is the result we have. Are you getting my point? Okay, it is not difficult to understand, but the application part is a bit difficult. Okay, clear? So keep that in mind. Okay, that's why I'll go slow and all the terms will try to understand properly, because if you have difficulty in first two lectures, you will have difficulty in the entire topic. Okay, so we have this piston. Now what we are doing, we are considering a system, a gaseous particle which is present in this system, right? In this container, piston cylinder system. We call it as piston cylinder system, which we'll use very frequently in this chapter to understand concept. What we call it as? We call it as piston cylinder system. So consider this as the air pump that we have, correct? Now what we can do, it's on us that we can fix this piston also, right? We can fix this piston, or we can keep the system like, keep this piston like this, that it can move up and down depending upon the external pressure, P external, Pxt means P external, and this is the pressure of the gas. So when these two pressures are equal, the piston will be static, it won't move, isn't it? Yes. If the piston is fixed, then also it won't move, because, and there's no any chances of, the shifting of the piston, up and down movement will not be there. Piston mass we are not considering. It's in physics sometimes we consider. Here we are considering piston is the massless. Mass we are not considering here. Okay, so take that assumption in mind. Okay, piston is massless. Correct. So This pressure and this pressure is equal. There's no movement in the piston, right? And if it is not fixed here, if you don't fix this piston over here, then you apply pressure, you increase pressure, the piston will come down, correct? Yes or no? Yeah. So the boundary is changing, right? The boundary is movable now. It is moving up and down. You increase the internal pressure, the piston will move up, correct? So this we call it as movable boundary, right? Understood? Movable boundary? Yeah. Fixed boundary is what? This piston, you fixed it. You fixed it, piston. You take a, block, iron container. That boundary is fixed. You can obviously you can change the shape by applying pressure, but boundary is fixed. Correct? That is a fixed boundary. This one is movable boundary. We'll have both kind of boundaries. Mostly you will have movable one, right? In the same. Now, imaginary is what? Now, suppose in the atmosphere, now, a static piston is not fixed. It depends whether you have fixed it here or not. Here you see P external is equals to P gas. The piston is static, but it can move up and down, right? Because we haven't fixed it over here. Right? If there is no clamp over here, then piston can move up and down, right? So that is not an static. That is not a fixed system, right? Fixed system will be mentioned in the question that we have this piston here fixed so that it cannot move, or clearly in the question it will be mentioned that we have a movable piston cylinder system. Did you get it? No doubt. Yeah. So fixed is and movable is. Imaginary is what? Suppose in the atmosphere we have oxygen gas, right? Could you identify the boundary of oxygen gas? No. Yes. We imagine no that the volume of oxygen gas is this. So this is the imaginary boundary we have. In this volume, the oxygen gas is present. So there's the imaginary boundary we are assuming. Yes or no? Are you getting it? In the atmosphere, whatever gas we have, we cannot see those things, correct? We cannot see the gas. We cannot, feel or imagine or see the boundary of the gas. And but we know the oxygen gas will have a certain volume, nitrogen will have a certain volume, methane will have a certain volume. So beyond that volume, we can have another oxygen molecule, but for one oxygen molecule, the boundary, the volume is fixed. Yes. So that kind of boundary is the imaginary boundary. We imagine it, right? Real boundary is all these things that we can feel, we can see, or we can, touch it, right? All these boundaries are real boundary. Now, adiabatic and diathermic is what? Adiabatic boundary is the boundary in which there is no heat flow, no exchange of heat. Okay, neither the heat can come in, now the heat can go out. Adiabatic is this. Okay, no heat flow. Understood this? However, we don't have that ideal, container. But yes, we have a thermoflask, right? The water bottle that we use, the thermos that we use, okay, thermoflask, that is a kind of adiabatic, you can say, right? It is not ideal one, but to a certain extent, you can understand from that. Okay, you keep hot water into that for like 4, 5, 6, 7 hours, the water is still hot, right? So that's what, because it does not let the heat go out of the flask that you have. That kind of boundary. Yeah, we can say delta Q. I'm not using this term delta Q equals to 0 because I haven't said that heat is represented by Q, right? You can say delta Q is 0, no heat flow from this. Okay. Diathermic, diathermic, wall is what? Diathermic wall is in which the flow of energy is possible. Write down. Opposite of this, flow of energy in and out is possible. Yes. Any doubt? Only one way, as in, Aditya? Okay, the question is it possible to have heat flowing only one way? Yeah, it's possible. One object at 100 degrees Celsius, correct? And other one at 10. So when you connect these two objects, the heat flows from 100 to 10, high temperature to low temperature, always. Yes, understood? So flow of heat totally depends upon the temperature difference. It always flow from high temperature to low temperature, always. Till the temperature become equal. Okay. The flow of heat will be there until the temperature becomes equal in both sides. Clear? Now, this is we discussed about boundary, what is system, what is surrounding, and what is boundary, what are the different types of boundary we have. Now, when you get the question, in question it will be mentioned, like we have an adiabatic boundary. So you should know the fact. What is the meaning of adiabatic boundary? No, this is fine. I won't dictate you all these things. Okay, you write down as it is written. Okay, definition is not required. All these things are important. That is what you need to know. Okay, we are not going to dictate it. So fixed you understood, mover you understood, imaginary, and this one, the last one is what? Real you understood. In the question you will get sometimes we have an adiabatic boundary. So what you should know? You should know, okay, boundary is adiabatic, so delta Q will be 0. There's no heat exchange. Boundary is diathermic, so there is flow of energy, right? Mass flow is not there, but energy can get exchanged. Okay, this information you should know. Okay, now you see this system is also classified into three categories. So write down the next line. There are three types of system we have. There are three types of system. The first one is open system. Open system is what? Suppose we have a container, open container simply. We have an open container in which some gaseous molecules are. See, we are discussing this with respect to gases only, but we can apply this for anything, solid, liquid, anything we can apply. But we'll take one reference just to take an example or to understand things. So mostly we are considering what? We are considering gases here. So this gas is the system, right? Since the vessel is open, then what happens? The gas can flow in and out, right? This exchange is possible. It can go out and come in, right? So this is the open system. So in open system, what happens? In open system, what we can say? There is, flow of mass, and energy. Both can get exchanged because surroundings are interacting, no? So molecules can skip into the surroundings and can come back into the system. Again, energy can also get exchanged with the surroundings because the system is open. So flow of mass and energy is possible. So if I write down here, energy is not constant because it is getting exchanged. So it is not constant, and mass m is also not constant. Okay. Another type of system we call it as closed system. In closed system, we have a closed container, simple, right? But again, we have gaseous molecules present here in the system. Again, the system is this gaseous molecule only, but the container is closed. So the entire system is the closed system we have. Correct? So this is the gaseous particle we have. Since the container is closed, So gas cannot escape into the atmosphere or surroundings, right? However, through the wall or across the wall, you can say there will be heat exchange possible, isn't it? Across the wall, heat exchange possible, right? So you must have seen that if you have a flask, only steel bottle flask, if you have, or simple like one steel glass, if you put hot water into it, you can feel the the heat outside the glass also if you hold it, right? Why? Because the heat is getting transferred through the or across the wall of the glass. Okay. However, the water is not coming out. Mass is there, constant, but heat is getting exchanged. Okay. So what is happening here? In this case, flow of flow of energy is possible, but there is no exchange of mass. No exchange of mass. So M is constant, mass is constant, E is not constant. Energy is not constant because it is getting exchanged. Copy this down. See, the total energy will be constant. No, Vaibhav. Total energy won't change. If the molecule collides, then either it will transfer the energy to this molecule or it will gain energy from another molecule. So there will be exchange of energy. Correct. One molecule, the energy will decrease. For the other one, energy will increase. Yes. Yeah, that is possible. Exchange of energy possible because of collisions. Okay. Apart from these two, we have a third type of system, which we call it as isolated system. Right now, in this type of system, the boundary is completely sealed and insulated. Insulated boundary here. There's no exchange, nothing is possible. Mass as well as energy exchange is not possible, right? It is completely isolated from the surroundings. There is no interaction with surroundings. So neither exchange of mass nor exchange of energy is possible. So M is not constant, mass is not constant, energy is also not constant. Oh, sorry, other way, no. Mass and energy both are not getting exchanged, so both are constant. Yeah. Done? Yeah. Now, based on all these, theory that we have discussed, some important statement you see, you just need to judge whether it is true or false. Okay. So now we are going to see true false statement. Important. Conceptually, it is important to understand. Okay. So you just need to find out which one is true, which one is false statement. First one, a closed system always has constant volume. Neither heat. First of all of you copy this down. There are 6 statements we have. All of you copy this down. And before answering the question, just think about it. Okay, don't simply answer the question. Okay, think about it. Neither heat nor matter is exchanged then the system must be isolated. Isolated system will be closed system. A closed system must be an isolated system. Okay, I'll go to the next slide. I'll go back, wait. Or just a second, I'll go back and we'll write down the same slide only. 1 second. An adiabatic container fitted with a movable piston, adiabatic, I'm sorry, movable adiabatic piston, adiabatic container, and piston is also adiabatic, will form an isolated system. And the last statement is an adiabatic container fitted with rigid adiabatic piston rigid adiabatic piston will be an example of closed system. So all of you must down all these 6 statements. All done? Okay, you can send the response now. Just you can write TF like that. Last 1 minute. Try this fast. Okay. So answer for this question is this one is false. Second one is also false. It's true. False, false, false. How many you got correct? Yeah. 4 correct. Okay. Let's understand this. Chalo, theek hai. So, first of all, a closed system always has constant volume. Not possible. Why? Reason? Because we can have movable piston, right? No constant volume here. Neither heat nor matter is exchanged, then the system must be isolated. Okay? neither heat nor matter is exchanged, the system must be isolated. This one is also false because heat exchange is possible with work done also, right? So work done possible here. Heat can be exchanged with the help of work done, right? So this is the answer here. On its own, the heat and matter is not getting exchanged, but when you do the work on the system, or if system is doing work, then in that course there will be an exchange. Okay, that is the explanation of the second one. The third one is isolated system will be a closed system. Obviously it should be, otherwise it won't be isolated, because isolated system is something like, there's no exchange of heat and energy. So this one is the simplest one. A closed system must be an isolated system. Okay, closed system must be an isolated system. Not possible, because isolated system there is no exchange of heat energy, right? But in closed system, what happens? Like we have piston cylinder system, we have movable piston, right? Where the piston can move up and down, and work done is again possible, right? So again, the answer is what? In case of movable piston, we have work done possible. So it cannot be the isolated system. Okay, the last two. Adiabatic container fitted with a movable adiabatic piston will form an isolated system. So what happens here? This is adiabatic container, adiabatic piston. So there is no exchange of heat, but piston can move up and down. So work done is possible, and hence the system is not an isolated system, but it should be a closed system, isn't it? This is a closed system, not adiabatic, not isolated system. Okay, last one, an adiabatic container fitted with a rigid adiabatic piston. It is an example of closed system, since the piston is adiabatic and it is rigid also, right? So it cannot move up and down, so work done is not possible. Hence it is an example of isolated system, not closed system. It is also closed. That's not a wrong thing here, because the system is completely closed from all the four sides. But since there is no exchange of matter, there's no exchange of energy, so it is an example of isolated system, not closed system. Closed system is something in which the exchange of energy is possible, but exchange of matter is not possible. Yes, the last one you're talking about. No, Mother, that's not correct. Isolated system is something that is completely isolated. No, definition is different, Pranav, in both. Definition is what? In isolated system, there is no exchange of matter and energy, right? Closed system, exchange of matter is not possible, exchange of energy is possible. So we'll go by definition, not by like, okay, it is closed and then it should be closed system. No, third one is also not false. See, if the system is closed, then it is isolated system, provided there is no exchange of heat or energy. Means for a system to be isolated, it has to be closed. That is a necessary condition. Okay, But if the system is closed, we cannot say it is isolated if there is a transfer of energy possible. You understood my point? I'll just tell you, go by the definition. Closed system is the one in which there is transfer of energy, there is no transfer of mass. Okay, right? When there is no transfer of energy or mass, it is an isolated system. Now, for a system to be isolated, it has to be closed. We can say all isolated systems are closed, but all closed systems are not isolated. That's why third statement is correct. Are you getting my point? You can write down these notes that all isolated systems are closed systems, but all closed systems are not isolated systems. Tell me, is clear?